In this video, I intend to demonstrate you how in just a few minutes a fluid mechanics problem can be solved by applying Bernoulli's equation to a real fluid. Since we have already several times commented, analyzed, and demonstrated the implementation of these steps used to solve this type of tasks, we are not going to waste time to repeat them again. Just to remind you, they are shown on the slide. And again, I want to say that if someone is still not aware of why and how the proposed methodology is applied, it can be understood in detail by watching the introductory video, link to which is given on the slide, as well as in the content below this video tutorial. On the next slide, on the left, it is presented the task work diagram, and on the right is the input data, which in other words means the information that is provided in advance. A system used to transport cold water with density of 1000 kg per cubic meter, which is considered as a real fluid, is presented. Water is transported between two tanks located at different heights, and the difference between the water levels in them is expressed by the height h. The connecting pipeline has a length of 18 meters and a diameter of 100 millimeters, and the ensured flow rate in the system is set to be 15.4 liters per second. The friction factor, also known as Mayer energy loss coefficient, lambda, is 0.025, and the coefficients of local resistances, also known as minor energy loss coefficients, are known in advance, and they respectively are: at the entrance it is 0.5, for an elbow 1 unit it is 0.25, for the throttle valve it is 4, for the Venturi tube, which is a basic flow meter, it is 0.2, and for the exit it is 1. The pressures in the two tanks are also known, as for the one on the left there is manometric pressure, which is 100 kilopascals, and for the one on the right, which is vacuum pressure, is 100 torrs. The unknown parameter to be determined is the height h. I always advise you at this point to convert all the parameters in the input data into their basic measuring units, which means to fulfill the so-called step 0. So, in this regard, the diameter should be converted into 0.1 meters. The flow rate should be converted into 0.0154 cubic meters per second. The vacuum pressure will be 13,330 pascals, while the manometric pressure will be converted into 100,000 pascals. Now we can move on to the step 1, which is the so-called known parameters, including the following actions. The first action is establishing a relationship between velocity and flow rate, as for this purpose the equation of continuity is used. This aims to determine the flow average velocity. So, do the following. Copy and paste the relevant equation. Substitute each parameter with its numerical value. And finally perform the calculation. It seems that the velocity is going to be 1.96 meters per second. The second action to step 1 involves the calculation of the energy loss represented in the form of head. For this purpose, we must consider in advance that the total energy loss represents the sum of the two types of losses mentioned before. So let's start with the estimation of the friction energy loss. Initially, the formula that can be seen on the slide is used. Then it is replaced with numbers, and after being calculated, it is obtained that the friction energy loss will be 0.88 meters. The calculation of losses in local resistances may be performed into the following way. The appropriate equation presented on the slide is used. All the symbols, parameters, are now replaced with their numerical values. Just remembering to multiply zeta k by 2 because of the number of elbows in this case, when expressing the total coefficient of local resistance. All that remains is to perform the calculation on the basis of which it is found that the local resistance loss is 1.21 meters. In order to complete step 1, it's necessary to go back a few rows higher and sum the values obtained for the two types of energy losses, thereby enabling the final calculation of the total energy loss in the pipe, and in this case it will be 2.01 meters. Now we can easily move on to the implementation of step 2. The step 1, I remind you one more time, is expressed in correctly selecting of two sections for which the Bernoulli equation, in the case of a real fluid, to be further applied. In order not to waste time, trace for the two ends of the height h, which will automatically take you to the places where they should be selected. In this case, this would be section 1.1, the water level in the left tank, and section 2.2, the water level in the right tank. Be sure to indicate the places on the diagram where the two sections are selected, as demonstrated in the sample work diagram on the slide. The next action is related to the description of the work parameters in the previously selected sections. Let me start with the absolute pressure. For section 1.1, since the tank is closed and manometric pressure is acting, the absolute pressure will be presented as the sum of the atmospheric and corresponding manometric pressure. For section 2.2, the case is analogous, but it should be taken into account that vacuum pressure is acting there, which means that the absolute pressure will be presented as the difference between the atmospheric pressure and the corresponding vacuum pressure. The velocity in both sections will be 0. It is known, I'm just reminding you, and should be remembered as a rule to always apply in such cases, that the velocity in the uppermost liquid layer, the so-called free level of water in the tank, is reliably small. In other words, it is assumed that the velocity v1 will be equal to the velocity v2, approximately equal to 0. To determine the values of z, the rule applies. For the section that is closer to the Earth's surface, z is equal to 0. And for the section that is further away from it, z is equal to h. In this particular case, closer to the ground is section 1.1, which means that z2 will be equal to h. I put question mark because we are looking for this parameter, while z1 will be equal to 0. Performing step 3 only involves rewriting, copy-paste the Bernoulli equation for a real fluid. It is time to move on to the step 4, where this step uses the data from step 2 and substitutes it into the Bernoulli equation. Again, I advise you to always make the initial substitution literal, which means symbolical instead of numerical, like presented on the slide. The parameters colored in orange are about to be truncated, eliminated, leading to a simplification of the equation. After removing the unnecessary terms of the equation, the following expression, final equation, is obtained. Next to do is the numerical substitution, after which the calculation is performed. In conclusion, for the unknown height, it is obtained the value of 9.54 meters.